Welcome to G-Fun Facts Online. Beneath our feet lies an awesome power, capable of reshaping entire landscapes. Volcanoes. For the 1 billion people living in the shadow of an active volcano, the pressing question is not if, but when the next eruption will occur. The key to answering that question lies in listening to the Earth itself. Today, we're exploring volcanic seismology, the science of using the planet's own tremors to forecast deadly eruptions. We'll delve into the symphony of signals that precede an eruption, the incredible tools scientists use to hear them, and the high-stakes world of predicting when a mountain might explode. So how do you listen to a volcano? It starts by understanding its unique language. Unlike the sharp jolts from tectonic plates slipping, volcanic earthquakes are a complex suite of signals. They are the sound of magma on its relentless journey to the surface. The most common type is the volcano-tectonic earthquake, or VT quake. These are high-frequency tremors caused by rock cracking under the stress of rising magma. Imagine molten rock forcing its way upward, shattering the brittle crust in its path. That's a VT quake. They often occur in swarms, hundreds of tiny events in a concentrated area. While most swarms don't lead to an eruption, they are a clear sign of volcanic unrest. Crucially, if scientists track these swarms and see them getting progressively shallower, it's a strong hint that magma is rising, dramatically increasing the odds of an eruption. Then there are long-period earthquakes, or LP events. These are much deeper, lower-frequency rumbles. They aren't caused by rock fracturing, but by the movement of fluids, magma, gas, and water, sloshing around inside the volcano's plumbing. Think of it as the sound of the volcano's circulatory system, the injection of new magma, the resonance of gas and deep cracks. All of this generates LP events. These are often a more direct indicator that something is moving down there. Months before the catastrophic 1980 eruption of Mount St. Helens, for instance, the volcano began producing a significant number of these LP earthquakes, an early warning of the disaster to come. When these long-period events happen so frequently and so close together that they merge into one continuous signal, it's called volcanic tremor. This is a sustained, rhythmic ground shaking that can last for hours or even days. Its appearance is a major red flag, often signaling that an eruption is imminent or has already begun. A specific type, called harmonic tremor, has a pure, almost musical quality. It's thought to be the sound of magma resonating in a well-defined pipe or chamber, a strong indicator of steady magma flow. This very signal was detected in the days leading up to the 1991 eruption of Mount Pinatubo, and it helped solidify the decision to evacuate. Beyond these main types, a volcano's seismic vocabulary includes sharp explosion quakes from pressure releases at the vent, the noise of terrifying pyroclastic flows, and even the seismic signature of lahars, or volcanic mudflows, which can be used for tracking and early warnings. To capture this diverse symphony of signals, volcanologists deploy a sophisticated arsenal of instruments. The workhorse is the seismometer. A typical monitoring network requires at least 6 to 8 seismometers, placed within a 20-kilometer radius of the volcano. For high-threat volcanoes, that number can double to ensure highly accurate tracking of earthquake locations. These networks use a mix of short-period seismometers, good for the high-frequency snaps of VT quakes, and broadband seismometers, which are essential for catching the low-frequency rumbles of moving magma. The data is streamed in real time to observatories, allowing scientists to spot changes the moment they happen. But just detecting these quakes isn't enough. The real magic is in the analysis. One of the most powerful techniques is seismic tomography. It's like a CT scan for a volcano. Seismic waves from earthquakes travel at different speeds through different materials. They slow down when passing through hot or molten rock. By analyzing the travel times of waves from hundreds of quakes recorded at many seismometers, scientists can build a 3D map of the volcano's interior. revealing the location and size of magma reservoirs. Another technique, moment tensor analysis, provides a mathematical fingerprint of the earthquake source, telling seismologists if the ground failed by simple cracking or if a fluid-filled crack was forced open, a direct sign of magma intrusion. While seismology is the cornerstone of forecasting, it's most powerful when combined with other methods. A truly reliable forecast requires a multidisciplinary approach. Geodesy, the study of ground deformation, is critical. As magma rises, it inflates the ground surface, often by just a few millimeters. High-precision GPS networks and a satellite technique called INSAR can detect this subtle swelling. GPS provides constant, real-time data from specific points, while INSAR creates broad, detailed maps of deformation over time. The combination gives a comprehensive picture of how the volcano is breathing. Scientists also monitor the volcano's breath directly through gas geochemistry. As magma nears the surface, pressure drops and dissolved gases like sulfur dioxide and carbon dioxide escape. A spike in SO2 emissions is a classic sign that magma is at a very shallow depth. Satellites and ground sensors constantly sniff the air for these telltale chemical changes. Then there's thermal monitoring. Rising magma means rising heat. This can be detected in hot springs, gas vents, or simply heated ground. Thermal cameras and satellite-based infrared sensors can spot these thermal anomalies, which might indicate that magma is getting dangerously close to the surface. When you combine all these data streams, an increase in seismic activity, a swelling of the ground, a change in gas emissions, and a new hotspot, the forecast becomes far more robust. It's this integrated approach that has led to some of the greatest successes in saving lives. The story of Mount Pinatubo in the Philippines in 1991 is a perfect example. After 600 years of dormancy, the volcano began to stir. A joint team of Filipino and U.S. scientists scrambled to install a monitoring network. They detected swarms of VT earthquakes under the summit, indicating magma was on the move. Tilt meters recorded the ground swelling. Airborne instruments measured a tenfold increase in sulfur dioxide emissions. Based on this converging evidence, scientists issued increasingly urgent warnings. As volcanic tremor appeared, they knew a major eruption was coming. A large danger zone was evacuated. On June 15th, Pinatubo produced the second largest eruption of the 20th century. It was immense and devastating, but the forecast was a triumph. An estimated 5,000 to 20,000 lives were saved, a testament to what happens when the science and the communication work perfectly. But for every triumph, there is a tragedy that reminds us of the stakes. In 1985, the Nevado del Ruiz volcano in Colombia erupted. The eruption itself was relatively small, but it melted the volcano's summit glacier, unleashing a series of deadly mud flows, or lahars. These torrents of mud and debris buried the town of Armero, killing more than 23,000 people. The tragedy is that this was a predictable disaster. For a year, the volcano had shown clear signs of unrest: earthquake swarms, steam explosions, and increased gas activity. Scientists had produced a hazard map that accurately predicted which areas the lahars would inundate, including Armero, but the warnings went unheeded. A combination of hesitant public officials, a lack of a clear warning system, and confusing messages led to a catastrophic failure of risk communication. By the time the danger was obvious, it was too late. Nevado del Ruiz became a brutal lesson that a perfect forecast is useless if it doesn't lead to effective action. Despite these advances, forecasting remains a massive challenge. One issue is the non-uniqueness problem. Different processes can create similar signals. Is that seismic swarm a sign of rising magma, or just hydrothermal fluids moving around? This ambiguity can lead to false alarms, which can erode public trust. Furthermore, some volcanoes just don't play by the rules. The 2019 eruption of Wakari, or White Island, in New Zealand, killed 22 people with almost no immediate, clear warning, highlighting the inherent unpredictability we still face. And even with a good forecast, communicating uncertainty is incredibly difficult. How do you tell a community there's a 60% chance of a devastating eruption next week, and what does that mean for their lives and livelihoods? The future of forecasting, however, is bright. Artificial intelligence and machine learning are becoming game changers. AI algorithms can sift through immense archives of seismic data, learning the subtle fingerprints of impending eruptions and identifying patterns humans might miss. New sensing technologies are also revolutionizing data collection. Fiber optic sensing can turn standard telecommunication cables into a network of thousands of virtual seismometers, providing an incredibly detailed map of ground strain. Drones are being sent into hazardous areas to collect high-resolution gas, thermal, and visual data without risking human lives. And the public is getting involved through citizen science. Smartphone apps allow people on the ground to report observations, providing a valuable supplement to instrumental data and helping to build community resilience. The Earth will continue to churn, and its volcanoes will continue to erupt. But we are not powerless. Volcanic seismology has given us the ability to listen to a volcano's heartbeat, to translate its rumbles into warnings. The challenge remains to listen ever more closely, to improve our interpretation of this complex language, and to ensure that when a sleeping giant begins to stir, its whispers are heard and heeded. It is a continuous, silent vigil, but it is one of our most vital defenses against the fiery power that lies just beneath our feet.